Picture a hotel with infinitely many rooms, room 1, room 2, room 3, on, with no last room. And tonight, every single one is taken. The sign on the door says, no vacancy. Now I show up in the middle of the night and I want a room. And here's my bet with you. The clerk will find me one, without throwing anybody out. Sounds impossible, the place is full. But watch, the guest in room 1 moves to room 2, the guest in 2 moves to 3. Everybody shifts exactly one room down the hall. And just like that, room 1 is empty. For me. And this is no parlor trick. It's a real thought experiment from a lecture hall in Göttingen in the winter of 1924-25. In a course on the infinite in mathematics, physics, and astronomy, a mathematician named David Hilbert built this hotel to show something bigger than any hotel, something about infinity itself, and about how reliably our gut instinct gets it wrong. Hold on to the question of what he was really trying to prove. And here's the strange part. For decades, nobody was even sure Hilbert ever said it. Before we go on, forget real beds and towels. This hotel is nothing but the numbers 1, 2, 3, 4 forever. No vacancy just means every number has its guest. And my little trick from a second ago, everyone shifts down one that handles a single guest. But I'm greedy. What if it isn't one person at the door, but a whole crowd? 5? 100? Go ahead, take the bet. You're going to lose it, and enjoy losing it. First, the honest question. Why does this work at all? A normal hotel with 100 rooms, all full, that's the end of the story. The guest in room 100 would have to move to 101, except there is no 101. There's a last room. The infinite hotel has no last room. However far right you look, there's always one more beyond it. That's why everyone can shift down without anybody falling off the end. The part is exactly as big as the whole. So, the 5. Easy. Instead of shifting by 1, everyone shifts by 5. The guest in room 1 goes to 6. The guest in 2 goes to 7. Rooms 1 through 5 open up. 5 new guests, 5 beds, and every old guest still has a room to themselves. 100 guests? Everyone shifts by 100. A million? By a million. Boring, right? Exactly. Finite numbers are just a warm-up for this hotel. Now let's really turn it up. A bus pulls up outside. Not an ordinary bus. This one has infinitely many rows, one behind the other, with no last row. And it's carrying not 5, not 1,000 guests, but infinitely many. Exactly as many as the hotel has rooms. A second infinity, wanting in. A full house, and an endless line outside it, trailing off into the dark. Be honest, surely now it's over. Your first reflex is probably just have everyone shift down infinitely far. But infinitely far isn't a room number. There is no room called infinity. If I ask which room you end up in, you have no answer, and that's not a solution, that's a disappearance. Every guest has to end up with an ordinary number on their door, one you can read out loud. So we need a move that sends every old guest to a real named room and still clears out infinitely many. And there is one. It's almost cheekily simple. The clerk says just one sentence to every current guest, double your room number. The guest in room 1 goes to room 2, the guest in 2 goes to 4, the guest in 3 goes to 6. Everyone lands in their even-numbered room, and every even room is taken. But look what just happened. Every odd room is now empty. 1, 3, 5, 7, infinitely many free beds, enough for the whole infinite bus. A full house just made room for a second full house. The clerk built nothing new, he just spread the same guests thinner. And the best part, this move isn't mine. It's almost word for word in Hilbert's lecture notes from back then, written up by his young assistant Lothar Nordheim, a physicist who'd later help lay the foundations of quantum mechanics. Hilbert told it exactly like this: all guests into the even rooms, the odd ones free. And he had a second picture ready, one almost nobody mentions. Here it comes. Listen to how Hilbert put it to his students, paraphrased from the notes. We assume the hotel has infinitely many rooms, 1, 2, 3, 4, each occupied by a single guest. To accommodate a new guest, the manager need only see to it that each old guest moves into the room with the next higher number. Plain, almost offhand. To Hilbert, this was just an example. He attached no great importance to it. No formal proof, no formula on the board, just an image everyone in the room saw instantly. You don't have to be a mathematician to feel it land. Funny thing, decades later, a famous physicist and prankster turned these very words into a footnote that fooled historians. We'll get to that too. Hilbert's second picture was a ballroom. Infinitely many couples are dancing, every lady has a gentleman. A new lady walks in, and the host can still find her a partner, even for infinitely many new ladies. It's the same as the rooms, everyone shifts along once, and space appears out of nowhere. No couple has to sit out, nobody's left standing alone. Two pictures, one idea. And now I push it to the limit. Not one bus, not 10, infinitely many buses, and every one of them packed with infinitely many guests. Let's make the picture sharp. Each bus is an infinite row of guests, and there are infinitely many such rows. Stack them, and you get an infinite grid. One row per bus, one column per seat. Infinite to the right, infinite downward. No sheet of paper in the world holds this grid. It blows past every edge, in both directions. Every point you could ever name sits somewhere in it, and there's always more past that. It feels like infinity times infinity, a crowd that seems a whole level bigger than anything so far. And here's the honest question that carries the rest of this video. Is there a crowd too big even for this hotel? First attempt, and it's a beauty. We use prime numbers. The old guests move into the powers of 2, rooms 2, 4, 8, 16. The first bus gets the powers of 3, 3, 9, 27. The second bus gets the powers of 5, 5, 25, 125. Every bus gets its own prime. The third bus the powers of 7, the fourth the powers of 11, on and on through the endless list of primes. Because every number breaks into primes in exactly one way, these rooms never collide. No guest lands in someone else's room. Nobody's left homeless. It actually works. But, and now look closely, room 6 never gets anyone. 6 is 2 times 3, not a pure prime power. The same goes for 10, 12, 14, 15, empty forever. The method houses everyone, but it wastes infinitely many rooms. Tidy is not the word. Can we do it with no empty rooms at all? It can be done without a single empty room. And the trick is a move I want you to remember. We walk through the grid in diagonals, one short diagonal, then the next in a zigzag. The first guest on diagonal 1 gets room 1, the next diagonal, rooms 2 and 3. The one after that, 4, 5, 6. That's how we sweep the entire infinite grid, diagonal by diagonal, handing out the rooms in order. No skips, no repeats. The snake touches every seat exactly once. Every guest from every bus gets exactly one room, and no room is left empty. Not one bed wasted, not one guest doubled up. Infinity times infinity fits perfectly into a single infinity. Remember this diagonal, it just saved us. In a moment, it turns against us. And from here, it feels like this hotel could swallow anything. A bus full of buses. Fits. One guest for every grain of sand in the desert. Fits. One for every second since the Big Bang. Fits easily. One for every fraction you could ever write down. Fits. One for all the whole numbers, positive and negative in one go. Fits. Any crowd you bring me, a crowd of crowds, a bus of buses, it doesn't matter, as long as you can somehow number them off. 1, 2, 3, I'll find room, every time, always works. And right at the moment you feel invincible, the last bus pulls up. Hold on a second. Everything we've housed had one thing in common. We could line the guests up. A first, a second, a third. A queue with no end, but with a clear order. Mathematicians call that countable. It's the name for any crowd whose members can be numbered off with 1, 2, 3, no matter how enormous. The whole bet rested on every crowd fitting into a queue like that. What if a crowd shows up that can't be lined up? The last bus looks just like all the others, but when the clerk reads the name tags, he freezes. Not one of them says 1, or 2, or 27. Every tag carries a real number, a decimal with infinitely many digits, 0 point, and then digits without end. Not a whole number in sight. Every guest is a point on the line, wedged between 2 others. Every real number between 0 and 1 is sitting on this bus, in its own seat, and with this bus, the trouble begins. Why is this bus different from all the others? On every bus so far we could line the guests up, your first, your second, your third, a queue with a clear order. With the real numbers you can't. There's no first decimal just past 0. Which one would it be? 0.1, 0.01, 0.001? For any of them you instantly find a smaller one, hugging 0 even closer. And there's no next one either. Between any two, there are already infinitely many more. This crowd is so dense that no queue can form. You can't even point to who should go first. And a hotel hands out rooms only in order. Room 1, room 2. It needs the queue. Still, be generous. Let's just assume it works out, somehow. The clerk forces the guests into a list. Room 1 gets a real number, room 2 the next, room 3 the next, an infinitely long guest list, one real number per room, marching down the corridor forever. Let's claim every real number from the bus appears somewhere on this list, in exactly one room. If that's true, the clerk has won. Now Georg Cantor, a German mathematician, the first to truly measure infinity, and the man we owe this whole mess to, asks one innocent-sounding question. Is everyone really on the list? Or can we find a guest who's guaranteed to be in no room at all? Not by hunting through the endless list, that would take forever, but by building one on purpose, a stowaway that no list on earth could ever contain. Cantor builds this stowaway digit by digit, and he builds him along the diagonal, the very same diagonal that saved us before. He takes the first digit of the first number and changes it, then the second digit of the second number changes it, the third digit of the third number changes it. Down the diagonal he goes, flipping every digit as he passes. Wherever the diagonal shows one digit, he writes down a different one. That is the entire rule. Out comes a new decimal, and this number can't be in room 1. There, it already differs in the first digit. Not in room 2 either, second digit different. Not in room n, the nth digit never matches. It differs from every guest on the list by at least one digit. It's in no room at all. Let that sink in. We assumed the list held everyone, and yet we could effortlessly build a guest who's missing. Whatever list the clerk writes, this trick always finds one he forgot. And if he squeezes that stowaway into a room after the fact, Cantor immediately builds the next one who's missing. There is no complete list. The queue the whole hotel depends on simply does not exist for this bus. The one tool that housed every crowd before is gone. For the first time, a crowd is too big. This bus has more guests than the hotel has rooms, even though both are infinite. The bet is lost, at last. This is the moment our picture of infinity changes forever. Until now, infinite was just infinite, one single kind of vastness. Now we have two, the countable kind, the rooms, the buses, everything you can line up. The natural numbers belong to it, the even numbers, even all the fractions, they're all the same size, as crazy as that sounds, and a bigger kind, the real numbers, which refuse to be lined up at all. Mathematicians call the first countable, the second uncountable, and the uncountable one is provably, solidly bigger, not by a little, but out of reach. Two infinities, and one won't fit inside the other. So how many sizes are there in total? The answer is dizzying. Cantor showed, for every size of infinity there's a bigger one. You can always build one so large the previous won't fit inside it anymore. A staircase of infinities that itself never ends. The reals aren't the top step, above them sits a bigger infinity, and above that a bigger one still. But we'll climb that staircase another time. Tonight we stay with the two, and with the man who found them. Because nobody was handed these two sizes of infinity for free. The man who found them paid a heavy price, not in money, in his health, and in his standing among his peers. He was attacked, openly and bitterly, by one of his own teachers, and it nearly broke him. Georg Cantor, a mathematician in Halle. In the 1870s and 80s, he did something almost heretical. He treated the infinite not as a vague on and on, but as something you can calculate with. He compared infinities by size. Before him, the line was, infinite is infinite, end of story. Cantor showed that was a far too crude answer. The diagonal trick we just watched is his, from the year 1891. He opened a door nobody had even seen before, a paradise, as it would later be called. But not everyone wanted to walk through. The resistance had a name, Leopold Kronecker. Once Cantor's own teacher, now his fiercest opponent. To Kronecker, only the finite was real mathematics. Cantor's completed infinities he considered nonsense, dangerous even, something you'd best not teach the young at all. He publicly called Cantor a charlatan and a corrupter of youth. Even the great Henri Poincaré joined in. Set theory, he said, was a disease that mathematics would one day recover from. Cantor, fragile as he was, suffered badly under these attacks and withdrew again and again, exhausted. Recognition came for his work, but slowly and late. And here the circle closes back to our hotelier. David Hilbert was one of the most powerful figures in his field, and he stood up for Cantor. In a famous address, he said one line that still echoes today: "No one shall expel us from the paradise that Cantor has created for us." The hotel was Hilbert's gentle way of walking you through the door of that paradise. That leaves the old question, did Hilbert really invent the hotel? It only became world famous in 1947 through a book by George Gamow, 1, 2, 3, Infinity. Gamow was a physicist, one of the fathers of the Big Bang Theory, and a gifted storyteller who wrapped even the hardest math in stories. He told the hotel as a story about the famous mathematician David Hilbert. And because Gamow was a notorious prankster, he added a footnote, citing a collected volume of Hilbert stories that never existed. That very footnote later threw everyone off. Because for a long time even historians thought maybe Gamow made the hotel up and pinned it on Hilbert as a joke. The historian of science Helge Krag argued exactly that, until a colleague pointed him to Hilbert's old lecture. When Nordheim's notes from 1924/25 finally appeared in print in the year 2013, there it was in black and white. Hilbert had told the hotel. Krag publicly retracted his own thesis, a guess about the past, overturned by a new find, the way you'd expect only in the natural sciences. So the name on the hotel is right after all. And the proof was in front of us the whole time. Remember Hilbert's second picture, the ballroom? That exact pairing, hotel and dance, sits in the notes. A prankster would never have invented the ballroom too. That was the tell. That leaves the very first question. What was Hilbert actually trying to prove? Not that hotels like this exist, quite the opposite. Hilbert loved Cantor's paradise as an idea, but he was convinced, in the real world, completed infinity does not occur. No infinitely many stars, no infinitely many atoms. Infinity for him lives only in thought. His own line for it. The infinite is nowhere to be found in reality. The hotel isn't a place, it's a tool, to walk your mind up to a boundary it would otherwise never touch. And that brings us back to our bet from the very beginning. A full hotel, and still room, for one, for 1,000, for an infinite bus, for infinitely many buses. Every time, I won. I only lost when a bus arrived whose guests couldn't be lined up. Not because the hotel was too small, but because some infinities are simply bigger than others. The house had a room for every countable crowd in the world, just not for the one that can't be counted. The hotel that never fills up showed us exactly that. Two words traded their meanings in this story. No vacancy never meant no room, and infinite never meant all the same size. The full house was never truly full, and the endless numbers were never truly all one thing. A hotel that will never exist taught us there's more than one infinity, and that the finest doors are the ones with yet another door behind them. If stories like this grab you, we've got a few more of those doors.